Hello class, today we're going to be looking at data representations in our Computer Foundations unit. Okay, now if you recall, we talked about how computers, they work on data, and all data is basically represented in some sort of binary number pattern. And it's somewhat arbitrary. I can choose if I want to. I could say, you know what, I want 000 to represent the value 0. I could say equivalently, no, I want 0000 to represent the value 10,000. Or I could say I want it to represent the value black, or I could say I want it to represent the value white. And it's fine. You know, the problem is if one computer wants to talk to another computer, they need to kind of agree on the encoding. You know, if I say it's 0, if I say 0000 is 0, but then somebody else says it's 10,000, that would be very confusing. If I say it's black and somebody else says it's white, that's very confusing. So what we need, the way we deal with this problem is that we need standards in computer science so that when I want to deal with color, we have an agreement that maybe, for example, 0000 is understood as black. And so it's not understood as accidentally by some other computer white. Otherwise, I make a picture on my screen, I send that picture to somebody else, and all the colors will be different. And we don't want that. So we have standards of how we represent data using different bit patterns. And so today we're going to be looking at different of those standards, different ways we represent data commonly in computers. Now, of course, numbers. Numbers is one of the most commonly dealt with data items in computers, and we've already learned how we could represent whole numbers. And so very standard way of representing whole numbers is using the normal place value system that we talked about the other day. And so we start with the number 0, and we just increment by 1, and in this case for 4 bits we can get all the way up to a maximum value of 16. With this kind of system, I can always get up to, depending if I have n number of bits, from 0 all the way up to 2 to the nth minus 1 values. Okay, in this case 0 through 15 when n is equal to 4. But how about negative numbers? How do we deal with that? Now, there are two standard ways we deal with it in computer science. One is what was called 1's complement, and the other is called 2's complement. Now, in 1's complement, we use the most significant bit, the leftmost bit, the MSB, most significant bit. We use that to indicate the sign. So this is what I mean. So say I have 5, and I want to represent both a negative and a positive value here. So instead of using a symbol, we're going to use a bit. So I have my binary value 101, and for the positive version of it, I'm going to put a 0 in front of it. But for the negative, I'm going to put a 1. So that's the idea of using the MSB. So that leads us to this table. I could represent my positive numbers here. I could represent my negative numbers here, all from 0 to 7, 0 through negative 7. Now, this is a pretty straightforward way of encoding it, and that's called 1's complement. There are a couple problems. One is that there are 2 zeros, and that's kind of, I don't know, a little annoying that I have a positive 0 and a negative 0. The other thing is that it adds strangely. It doesn't add, you could say, normally. So if I took 1 and if I took negative 1, and if I wanted to add these together, 0, 0, 0, 1 plus 1, 0, 0, 1, what do I get? If I add it kind of in the normal way, I get the following, and I get the answer -2. I get the result that 1 plus -1 is not equal to 0, but it's equal to -2. And that's also annoying and inconvenient. There are ways to work around it, but it's not normal. So today, most computers do not use 1's complement as a way of storing negative numbers. They use what is called 2's complement. This is the standard encoding for negative numbers in all computers that we talk about today. So, what's 2's complement? It uses the most significant bit still as a way of indicating signs. So 0 means positive and 1 means negative. But notice this. Instead, it goes from -1 all the way to -8. Kind of in a different ordering here. So the nice thing about this is adding is actually very nice. Let's try it out. Let's add up 1 and -1. 0, 0, 0, 1. 1, 1, 1, 1. If we add this up, we get the following. 1, 0, 0, 0, 0. We get this extra bit here, which is kind of like an overflow bit, but we just ignore it in the case of adding positive and negative numbers. We kind of toss it away, and we're left with our result, which is 0, which is what we would expect when we add, 1 plus -1. All right, how do we deal with fractions? There are two ways to deal with fractions. One is what's called fixed point, and the other is called floating point. In fixed point, what we are doing is we are fixing the decimal point in a particular place, in a place that we have specified it to be. So for example, I could have an 8-bit value, and I could choose to say my decimal point will be right in the middle. And we use the place value system to redefine the meaning of these bits. So this is 2 to the -1, 2 to the -2, 2 to the -3 in value. So if I have this number represented, I add up 2 plus 1/2 plus 1/4 to get my fractional value, 2.75. So this is one way to represent fractions, one way to represent real numbers. There's an issue, and the issue is kind of twofold. One issue has just to do with fixed point, floating point in general. So kind of whatever system we look at, we have this issue where, how do I write 0.6? If I use these 4 bits, it's a little too small. If I use these 4 bits, it's a little bit too big. So it's somewhere in between these two values. So maybe I need more bits. So I could extend it out, add more bits. But even with more bits, it's still not quite right. Not exactly 0.6. And the thing is this is a very important point. Just like it is with decimal values, there are just some fractional values that cannot be represented with a finite number of decimals. So if I have 1/3, for example, in decimal world, that's written like this. It goes on forever and ever, and I need an infinite number of digits to represent the value 1/3. Same thing with binary. There are certain values, actually many values, that just require an infinite number of bits to represent it. So there's always going to be a precision error, a precision issue with kind of real numbers. The main issue with fixed point, though, I would say is this. If I have a 16-bit fixed point value and I just arbitrarily put the decimal point right in the middle, I have 8 bits to the left of the decimal point, 8 bits to the right, and if I have 8 bits to the left, that means I have, I could represent up to kind of 2 to the 8th. So I could represent numbers from 0 all the way up to 255. So my max value is somewhat small. I wish, with 16 bits, this is actually not a very big number. And so the more significant issue with fixed point, I would say, is its somewhat limited range. So we move to another idea. Another idea is what is called floating point. And this is what's used, I would say, more normally. Computers, of course, still use fixed point. We can still do that. But it also has what's called floating point. Now in floating point, we have, let's look at kind of the decimal version first. It's like scientific notation. 5.123, you notice I'm using 4 digits here. And I'm using 1 digit for the exponent. And this represents a pretty big number, 50 billion. I could also represent a pretty tiny number as well, using the same number of digits and the same number of digits for my exponent. So just imagine I have a range of, from 0 to 50 billion using 4 decimal digits. And in that same kind of conceptual way, I can do the same thing with binary. I have this portion here, and then I have an additional exponent portion here. Let me write that in binary. So with these 5 bits here and these 4 bits here, I'm able to represent a much larger number. So that's the idea of floating point. Floating point really is a scientific notation form. The advantage of it is I could have a much wider range of numbers, from very small numbers to very large numbers. So here are the details of the format, and I'm not asking you to memorize it, but what I want you to see is how I can have 32 bits, and I kind of take a portion of it and use that portion to indicate my sign, use another portion to indicate my exponent, and another portion to indicate the fractional value. And so this number right here is another way of writing this decimal value. To get more precision, I could have 52 bits for my fraction. To get more range, I can use 11 bits for my exponent if I use 64 bits instead. Now, it used to be, there was a day, say 20, 30 years ago, when doing floating point math just required a lot of transistors, a lot of logic gates to implement it. It would almost take as many gates as a CPU, and it used to be too expensive. But nowadays, with such tiny transistors, gates are cheap, and now it's just common for all processors to handle not only single precision addition and multiplication, but also double precision. So the bottom line on floating point, remember 2 things. Remember that we cannot, it's always approximate. We cannot represent some values perfectly in a finite number of bits. There always will be associated with it some amount of error that you need to understand. Don't depend on it being exactly correct. Precision-wise, if I have a 32-bit floating point, I have approximately 6 to 7 significant digits to the right of my decimal point. And if I have 64 bits, I have even more. So, I could have 0.1276397, blah, 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 up to 15, 16 digits. So pretty precise. Now, in general, we just use 64 floating point unless memory really is a premium nowadays. Okay, let's look at some other data formats. Numbers aren't the only thing we want to represent. We could also represent letters, characters. So if I wanted to spell my name out, what do I do? Well, originally there was kind of a code called ASCII code where it used 8 bits for up to 256 different letters. And so I could use the, say, hex value of 41 to represent the letter A. And notice there's a decimal column and a hex column as well as an octal column. So we have the decimal 65, the octal 101, which is equal to the hex 41. That means the letter A. So 1 byte, 8 bits, is used to indicate one letter. So if I wanted to spell out my name, I could just use a table. And I'd look it up and I'd find, this ASCII table, not something you memorize. You just use it, look it up. And this would be in hexadecimal, my name. Now, that works pretty well for the English language. 52 upper and lowercase letters, some digits, some punctuation marks, 256 letters, pretty sufficient. But what about other languages? How do we deal with that? We can expand. We need more bits. So a new standard was made called the Unicode standard, and it uses 16 bits. So now that could get us 65,000 different characters. And we could keep going with this. We can go 32 bits. An extended Unicode is what they call it. And now, not only can we do all sorts of different languages, we can even do emojis. So this is an extended Unicode value for your happy face. And then on days when you're not so happy, days when maybe you've ate something wrong, this is the emoji for not happy face. I ate something bad face. So yeah, 40 or 4 billion different characters can be kind of represented with 32 bits of extended Unicode. Okay, how about other data? Pictures. Pictures, the way we create or represent pictures is by breaking it up into little tiny pixels of color. And in the old days, you could say, many, many years ago when computers were first coming out, memory is expensive. And we barely even have the ability to put color on the screen. And so it was just a matter of black and white, on or off. So you only need 1 bit per pixel. Maybe 1 is the value white, 0 is the value black, for example. Then we had the idea, well, oh, we can add kind of intensities of black or gray. Different scales of gray, light gray, darker gray. So if I wanted to, with 2 bits, I can get 4 different variations. I can go, very commonly you might have 4 bits, or you might even have 8 bits of gray shading, gray scale. But nowadays color is pretty standard everywhere. And the way color is represented is by looking at the intensity of the different components, the red, the green, the blue component. Now, when memory was a little more costly, the RGB value was fit inside 16 bits, and the top 5 bits were allocated for red, the middle bits were allocated for green, the bottom bits were allocated for blue. But now memory is very cheap, and so we go up to 24 bits for every pixel, 8 bits for red, green, blue. We can even go up to, say, 10 bits per, so we have 30 bits per color. Again, 10 bit for red, 10 bit for green, 10 bit for blue. Beyond that, I don't know how much is necessary. At some point, you don't get much more kind of fidelity. It's hard to create a TV screen that can have that many different shades of red and green. Sound. How about sound? Sound, I've mentioned this before. Sound is a is a wave of air kind of vibrating a magnet, and that magnet, as it vibrates, creates electrical current on a wire, and it goes up and down the electricity. So in a sense, sound is electricity. It's voltage level over time. So we can represent it as a waveform, voltage over time. And how do I represent a waveform? Basically, I just sample at different points of time. -4 right here, 0 right here, 4 right here. If I want a better waveform, if I want better sound, maybe what I'll do is I'll sample more often. Maybe instead of just sampling here, I'll add another point right in between, and I'll add another sample point right here. You know? So the more I sample, the better my waveform shape is. The other thing that improves my sampling is how many bits do I use for every sample. Here I'm just showing, the values from -8 to 7 in very discrete values. Not a lot of different bits. But I could use 16 bits to get, 65,000 different levels of voltage. And that, again, is going to give me more kind of high fidelity sound. So basically, the more often I sample in time, the better. CDs sample at 44,000 kilohertz. And then I have how many bits per sample. The more bits I use for every sound sample, the better as well. Okay, so that's my presentation. Hopefully you got this picture, this idea of how we represent data, all sorts of data, using these different standards that have been put in place. Okay, have a good day, everybody.